Welcome to Mr. E Science Theater presents Multi-Object Systems. Here we have a scenario where we have two blocks, A and B, that are attached by a string. Block A is resting on a table, block B is hanging off the edge. Assuming there's no friction, if we were to let go of the system, B would accelerate in the downward direction, and A would accelerate to the right. So that's the direction that they would accelerate. So if we want to find the acceleration and the tension in the string, there's a couple of different ways we can do it. The first way I'm going to show you is what we call a two-system approach. In other words, I treat object A and object B completely separately, and I'm going to work them out that way. So I begin by doing a force diagram for object A. So object A, we've got force of gravity down, of course. There is a tension force to the right. A normal force up. And there's no friction, so there we are, we're done. So then for object A, we do, next step, we write our equation. Net force equals mass times acceleration. We then identify by name the individual forces that make up the net force. Since A is accelerating to the right, we have the tension force is affecting the acceleration. In other words, in a go minus stop kind of situation, tension force is in the go direction, there's nothing in the stop direction. And so we just have the tension force equal to mass times acceleration. And last step, we can plug in our numbers. We don't know the tension. We do know the mass of block A is 5 kilograms, and we do not know the acceleration. So I get to this point, that's as far as I can go. So what I'm going to do next is I'm going to go to block B. So for block B, again, I'm going to do the force diagram here for B. We have a force of gravity down and a tension force that's up. And block B, I know, is accelerating in the downward direction. So when I do my net force equals mass times acceleration here, it's going to be down minus up. That's my go minus stop direction. So down I've got Fg minus my Ft equals m times a. Again, always identify them by name. You get those names right from your force diagram, so make sure you're putting the names on the diagram. Then we can plug in our numbers. So 1 kilogram means that Fg is going to be 10 newtons, minus the tension, which I don't know, equals the mass of block B, which is 1 kilogram, times the acceleration A. And again, I'm stuck because there's two things I don't know. Fortunately, it's the same two things I don't know over here. Because the system is tied with the string, the acceleration of A to the right is going to be equal to the acceleration of B downward. And so, if the tension is equal to 5A, I can substitute that in over here. 10 minus 5A equals 1A. And then to solve, I add 5A to both sides. 10 equals 6A. 10 divided by 6 equals A. And so my acceleration is simply 10 divided by 6, or 1.67 meters per second squared. That's my acceleration. Okay? Now how do I find the tension? I'm going to take this and plug it back up here. The tension is equal to 5 times A, so the tension in the string is equal to 5 times 1.67. So I multiply that out, and I get 8.35. Tension force, 8.35 newtons. That is the two-system approach to solving a multi-object system like this. Now, the other approach that I can take, I call it the single system approach. For the single system approach, what I would do is I would draw my force diagram a little bit differently. So for the force diagram for a single system, I'm going to treat the whole thing as a system. Draw a little dotted line surrounding my system, like so. And then I'm only going to draw outside forces that act on my system. So over here I've got a force of gravity of B pulling down. Here I've got a force of gravity of A pulling down, and there's a normal force on A, and that's it. There's no friction, so that's it. So when I do net force equals mass times acceleration in this case, B still accelerates down and A still accelerates to the right. So to the right is the go direction for A, and to the left would be the stop direction. For B, down is the go direction and up is the stop. So as I'm looking at my net force, my go minus stop, I've got the force of gravity of B in the go direction, and nothing is in the stop direction. Notice the normal force and the force of gravity of A do not affect the acceleration in any way. So I've just got the force of gravity of B equals m. Now what m do I use here? I need to use the mass of my system. Since my system includes both blocks A and B, it's got to be the mass of block A plus the mass of block B times the acceleration of my system. So now I can plug in my numbers. This is 10 newtons. My combined mass is 5 plus 1, 6, and you can see it's the exact same thing we got over here. 10 was equal to 6a, so 10 over 6 equals a, or 1.67 equals the acceleration. And once you have the acceleration, then, if you did the single system approach to find the acceleration, you would then need to split off and pick either A or B, and with this acceleration value, plug into the formula and solve for the tension. So we could look at it just like this, and I can see that the tension would equal 5 times A. I would plug in this acceleration value there and get it. Or I could look at it this way. I could plug in my acceleration of 1.67 here, and 10 minus the tension equals 1 times 1.67, and solve for the tension that way. So in a split system, I draw them separately. I do F equals ma for both. I get down to the point where I have the tension and the acceleration, then I'm going to substitute and solve. Plug the tension in to the other equation, solve for A, and then plug back in here to get the tension over here. In the single system, I do the single system using the whole mass of the whole system to find the acceleration. Once I have the acceleration, then I need to split one or the other and plug in the known acceleration to find the tension force. And that is how you do a multi-object system problem.